Cool. All right, we're recording. So what are neural networks based off of? So they're fundamentally designed based off our neurons. So we all know our brain is made up of neurons and all these interconnected cells that basically build up the network that is our brain. So neural network of neurons, kind of, that's how it's, because it's like we make decisions with these neurons and like the firings and the connections. So the idea is kind of basing it off of that. So this is what an actual like a basic neural network looks like. So there's the inputs, the hidden layers, and the outputs. So the way you can think about this is, so far we've gone over linear regression and logistic regression. Those models are inputs, weights, and outputs. So you can think of logistic regression and all that stuff as like essentially like a one layer network. Like you only have the inputs and the outputs. You don't have all these quote unquote hidden layers. What these hidden layers basically are just more sets of weights and connections and functions. So previously we've gone over having one set of inputs, weights, and then outputs, but now we have multiple layers where there's multiple inputs, outputs, and then you basically keep feeding that forward until you get the final output. So that's what it looks like. So the input layer, as you can see, there's input 1, 2, n. Those are essentially like the variables we've gone over, like multivariable models where you have multiple things that affect the model. So that's what the input 1, 2 to n are. That's the input layer. The output layer, output I through n. Usually if we're doing like binary classification, it would just be 1. It'd be either 1 or a 0. If we're doing linear, it'd just be a linear model. But sometimes there's something like classification where you output probabilities of classes, and then you'd have multiple outputs, which are the probabilities of each output. But yeah, and then these hidden layers. So what do these hidden layers represent? So each of these little dots in the hidden layer is a node, okay? So we call those nodes. Then each vertical layer of nodes is a layer. So you see this layers H1, H2, and all the way up to Hn. Then each of those little lines between each node is a connection. And those are essentially weights. So this is kind of what it looks like, right? So you have input 1, input 2, and input 3. And then you have, so those are nodes 1, 2, 3, 4, 5, 6, and then the final output is 7, okay? So how this works is the input is so each input is connected to each node. In this case, they didn't connect 2 of them, but you see that input 1 feeds into 4 and 5, input 2 feeds into 4, 5, and 6, and then input 3 feeds into 5 and 6. You guys see that? So that's kind of like information flowing into those nodes. And then each node, each of the connections is like a weight. So say 1 is like a number, 2 is a number, 3 is a number. When 1 goes to 4 and 2 goes to 4, they're multiplied each by one of these little weights, and then they're added up. So it's the same thing as like we've gone over with linear regression, where you have the weights and the inputs, except this is done multiple times per layer, and each connection is a different weight. So 1 and 2 are fed to 4 and multiplied and added together, and then 2 and 3 and 1, 2, and 3 are fed to 5, and each are multiplied by a weight and added up. And then 2 and 3 are multiplied by weights and added up to get 6. And then that's how you get the values for 4, 5, and 6. You guys get that? So it's like its own little like regression right there. Like you do a little multiplication with weights and inputs to get a value. So yeah, and then so then you just, that's kind of how the connections and the nodes work. So each node is like its own little model, and then they keep passing forward information. So we'll go more into the terminology. So okay, so here's why it gets a little complicated and looks weird. So okay, so this is like linear algebra right here. I'm gonna try to explain this best I can. So do you see how these are I's? So these are referred to as inputs. So it's I1, I2, I3, I4, I5, I6, I7, I8, I9. What does that mean? That means there's 9 inputs. So regardless of the layer of the neural network you're in, these could either be like the initial inputs of the neural network, or this could be like medium inputs in the layers, which are called activations. So this is either like the total input for the entire neural network, or this is just like one of the intermediate inputs. So what we're doing here is these are the inputs, and then each row of weights is one node, okay? So this is like nodes. You can see it's 1, 1, 1, 2, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, because this is node 1, then this is node 2, this is node 3, node 4, node 5. So that means that this layer, this is a linear algebra representation of a layer of 5 nodes with 9 inputs before. because you have 9 i's, which means 9 inputs, and then you have 5 rows that you're. You guys remember how multiplication works, right? Row multiplied by column. So that's what this is going on right here. So we're multiplying the row of weights into the column of inputs. And then what that gives you is if you dot the first row of weights by the column of inputs, you get a single value, right? Because it's 1 by 9 times 9 by 1, you get a 1 by 1 output. So 1 output. And then you see total input to H1. So that's the first output of that node. And then you move on to the next node, weights by inputs, another value for that node. Then you keep doing that for each node. So then this gives you the values for each node. And then from then you would also then apply like an activation function, but we're going to go into that later. But this is basically like so you can think of each weight and input like together as a line. So if we go back earlier, so each input is one of these, right? 1, 2, or 3. And then each weight is one of these lines. And then each of the outputs is one of these nodes, right? See, each weight is a line, each input is one of the inputs, and each of these outputs is one of the output nodes, right? So that's how it works. So this is so if we were to draw this out, it would be 9 inputs. So instead of 1, 2, 3, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you would have 5 nodes on the right. So it'd be like 10, 11, 12, 13, 14. 10, 11, 12, 13. Yeah, 10, 11, 12, 13, 14. And then every single one would be connected because that's what this indicates. Do you guys kind of you guys don't have to like perfectly understand it, but you guys kind of get the grasp of why that is? Okay. Yeah, don't guys, this is like pretty complicated, so don't worry if you don't really understand it that well. Okay, so like just quick review of matrix multiplication. You guys remember this, right? So if we multiply this together, it's rows of A multiplied by columns of B added up. Okay, so now we're going to go to activation functions. So what are activation functions? So we previously went over how when you have like logistic regression, you do essentially the same thing with linear regression, and then you plug it into the sigmoid function, so you get an output that's either 0 or 1. With neural networks, it's the same thing. So previously, remember, so we have this, right? So we have the weights multiply the inputs, and you get the activation. You get this Z or this output in the node. Then what you do with neural networks is then you apply an activation function. So instead of just having 0 and 1s, neural networks have multiple types of activation functions. So you can still do sigmoid, either 0 or 1. You can do tanh, which goes from -1 to 1. The popular one is ReLU, which is anything less than 0 is either 0 if it's not, you just keep it. And then so it's important because this adds non-linearity, so it's not just like a stack of linear functions. So it means like the neural network can find more complicated patterns. But this is what I mean when I say that like a neural network is essentially stacked up and layered like logistic regressions and linear regressions. Like you're basically doing these weights times inputs and then throwing an activation function multiple times per layer for each node, and then multiple layers. So it's like stacking these up. So it's basically what we've previously learned, just much more complicated, like just like on a more complicated scale, on a larger scale. Do you guys understand that? Okay. So here's what a single node looks like, right? So you have the inputs, say there's only 2 inputs, right? So you multiply it by the weight 1 and weight 2. So then you get weight 1 times x1 plus weight 2 times x2. And then you have the bias. Remember we've talked about having the bias, which kind of just shifts things up and down. And then what you do from there, so that's like the input into the node. Then you apply the activation function to it. And that's what this F is. So it's F parentheses of that. So what we call then Y, the output of the node, is either called like the activation or the output. So usually people call it the activation because then you send it to the next layer where it's then used to then activate, quote unquote, activate that layer. Yeah, so that's kind of what's going on here. And then remember, so we repeat that for every node in each layer and every layer. So yeah, the output of the neuron is the activation function on every weight times every input plus the bias. So that's done for every single node in every single layer. And then you pass that forward. So then for each node, once again, you have the inputs 1 through xm. Well, the 1 would be the bias, so it's 1 times W naught. And then x1 through xm, you multiply them by the weights, add them up. And then usually people call this Z. Just for like machine learning notation, the input, which is the weights times the inputs, is usually called Z. And then the activation function applied to that is called the activation. So that's A. So then you have all the biases plus the weights times the inputs. That gets a net input function. Then you apply the activation function, and then you get the output or the activation for the next layer. Yeah, so the input's a vector of parameters of activations from the previous layer or the vector of the inputs. And you matrix multiply that by the weights, and yeah. And then you apply the activation function, and then you get the output for that node. And then you repeat that for every node in the layer. So each layer receives the values from the previous layer. So that can be a previous layer of the neural network, like it receives the activations, or it can receive the total inputs of the data. It can just receive the input data. And then the input, it's a vector it's essentially a vector of data. And then the output of each layer is the activations to the next layer. So you essentially think of it as you're giving inputs into a layer, then that each node in that layer pops forward a number. And then that list of numbers from the nodes is essentially treated as another set of inputs for then the next layer. And then that's repeated until you get to the final layer, where usually it's one node or like a SoftMax, which is classification. And then you get the final output prediction. So that's how it works. And as you can see, for basic neural networks, most of the times it's just fully connected, which means all the input nodes are connected to the next layer's nodes. So this is what we mean when we say like each node has its own set of weights for all the inputs, and you just do tons of like multiplications to then get the outputs for that layer. Do you guys understand? This is why it's like all linear algebra, because you're just doing tons of matrix multiplications and like dot products and stuff like that. Okay, so then so the math for each layer. So here's like another example of the math for each layer. So we have the inputs, which are x1, x2, x3, and x4. And so you can see here that this is fully connected. So the blue node is like the first node in the second layer, green node, second node in the second layer, orange node, third node in the third layer. So you see that each node has a weight for each of the inputs, right? So the first node, A1, has weight 1, weight 2, weight 3, and weight 4 for x1, x2, x3, x4. Same for A2 and A3. So then you have also the biases for each node, the blue B, green B, and orange B, like we went over. And what you're doing in order to get the activations for the next layer is you're dotting them together, right? So you're multiplying W1, W2, W3, W4, X1, X2, X3, X4, and you're adding B, and then that gives you activation 1, because that's a single value, right? Because it's a 1 by 4 multiplied by 4 by 1, so 1 by 1 output. And then you repeat that for each row of the weights matrix, dotted by the column of the inputs, add the bias, and then that gives you 3 output values. Because there's 3 nodes in the next layer. Even though there's 4 inputs and there's 3 nodes. Does that make sense to everyone? Yeah, so that's how this works. That's a single layer. And then so then hypothetically what the next layer would be is A1, A2, and A3 would essentially be the X1, X2, X3, and X4 of the next layer. And then the next layer would have its own set of weights, but instead of having 4 weights, W1, W2, W3, W4, it would only need to have 3 weights because there's only 3 inputs of the 3 activations. Does that make sense? So basically, it's just sequentially, it keeps having this sort of math done. But also just saying, then there would have to have an activation function applied here. That's not shown, but you wouldn't just put, oh, well, it is shown. Yeah, so you see that the arrow activation, that's the activation applied. So the activation function is then applied to W1, X1 plus the bias. And then you get the activation 1, activation 2, activation 3, which is then passed forward. So it's a bit of a process for each node and each layer, but that's why they're like, it's a pretty complicated concept because it involves like a decent amount of math. So network progression. So so the parameters for the samples are the input, and so each node of the first layer receives a vector, and it applies its own weights and biases to get the activation value, and then this is repeated for every single layer until the last layer when you get the output. So it's called like feed forward. So like it takes values, applies the math, feeds it forward. Then the next layer takes the inputs, applies math, feeds it forward, and then it just keeps moving forward till you get the output. Okay, so hidden layer summaries. So so this is not the input layer. So all layers take the previous activations or the outputs from the previous layer, then each node applies its own weights, bias, and then it has an activation then using it like doing the math on the activations from the previous layer, it then gets its own activation, which it passes forward to the next layer. And like I said, this keeps going, happens, and it keeps doing this over and over again for each layer and each node. So output layer. So once you do this, depending on how many layers you have in your neural network, eventually you'll get to an output layer, which usually is either like I said earlier, a single node or multiple nodes, depending on if it's like what type of thing you're trying to do. But this is basically the final layer and determines like your quote unquote output. So what we're doing here is, for instance, say okay, so look right here. So say x1, x2, x3, x4, x5, x6, x7 is the final layers activation, or like the second to last layers activations. So then what you do is, so so here in the example, it's a sigmoid activation. So what we'd be doing here maybe is like binary classification, right? So we're deciding between 0 or 1, yes or no. So that means our final output wants to be 1 or 0. So that would be binary classification. So we yeah, so nodes, what the A or activation means is we call the value that a node outputs the activation. And then so when we say the activations of a layer, it means like the outputs of the nodes in that layer. And then so that the activations of one layer are then passed on to the next layer. So those are called activations because they like activate the next layer, quote unquote. Yeah, so with neural networks, right, you have the inputs, you have the weights, and then the activation function. So this is what this shows right here is essentially like a logistic regression, which is like you're applying a logistic regression on the last layer's activations. So that's basically what it is. It's just like you have one final node that determines the output, and that's what this kind of shows. Yeah. So sigmoid activation, I mean, the whole point of, well, no, so some people also use sigmoid activations in like the intermediate layers, just because, but they've kind of found that the ReLU or like the 0 to like linear works better. But yeah, if you're doing like a binary classification output, then the sigmoid makes the most sense because it's most representative of the results, either 0 or 1. So yeah, it's mostly just used for binary classification, but there's a bunch of other ones. Okay, I don't know if I'm gonna go over this because I don't really want to burden you guys with calculus, but basically so we've gone over previously that I've never really gone through the math of this, but I've always just kind of told you guys that you basically can use like a cost function or an error function, find out how much you need to change the model by, and work backwards and basically adjust the weights. So that's for linear regression and logistic regression. For neural networks, it's essentially the same process, but 100 times worse, because now you have to work through every single node and then go through all the nodes to all their weights and connections, and then go from all those weights and connections to go even back. So it's like, it's a much more complicated process. I'm not really going to go over that with you guys because it's a little too hard. So I don't even know if you guys like know what these symbols are. It's just like chain derivatives, and yeah, it's a lot of calculus, and you keep taking derivatives and passing things backwards. But yeah, so here's kind of like a simplified understanding of, because once again, you don't just have a good model starting out, right? You have a random model that doesn't perform well, and you essentially have to work and like keep adjusting the weights to get to a better model. So this is kind of like a simplified version of what it actually is. What's a derivative of a weight? That's like a calculus thing. Like I said, it essentially tells you like how much change there is. It's like so for instance, a derivative is like instantaneous change almost. So for instance, if you're taking like the derivative of a graph, you're saying like at a point, how much is the slope changing? It's weird. It's basically like how much change is there, and like what direction is the change, essentially. So it's like, what direction do you need to change the model, and by how much to get a better model? That's what that means. So that's what kind of the derivative means. So what we're doing here is you give the inputs the weights, and then you apply the activation function, and then that gives you, and then you repeat that for all the layers and all the nodes. You get an output, and then what you do is then you apply the cost function. So that's what's saying calculation of cost function. And then using the cost function, you would then do chain derivatives to get updates for how much you need to adjust the weight, you would then change the weights, rerun the entire model, get the cost function again, and then just keep adjusting it until you get the best model. Okay, I'll send you guys it later. Okay, so this is what we mean by the cyclic nature of training a neural network, right? So you have the inputs, you do forward propagation, you take the inputs, you feed it to all the nodes, and the nodes feed it to the next layer of nodes, and the next layer of nodes, and the next layer of nodes. Then you get the output, you get the predicted output for that network. You take the loss function or the cost function with that specified what it should be, and then you do backwards propagation by doing derivatives and all that fun stuff, and you get how much you need to adjust all the weights. You adjust the weights, then you get the next prediction. It's still not perfect. You do it again. Keep going until you get the best model that you can get. Then you say, okay, we have the best model. Then you just keep going. So yeah, that's kind of what that is. So so it's just a bunch of compiled matrix multiplications and activation functions, and you use like chain derivatives to fix and find the direction of change to minimize the error of the model. So yeah, that's kind of just the quick summary of like neural networks. It's like, I don't expect you guys to like understand it immediately. It's like pretty complicated stuff. Do you guys have questions? Okay, so forward propagation it's not a single equation, right? So forward propagation is like equation stacked. So you're doing one calculation, so one equation for each node. And then you have multiple equations because there's multiple nodes per layer. And then you take the outputs of those equations and pass it on to the next layer, then the next layer, the next layer. So that's forward propagation. What back propagation is, you're taking essentially how far away is our prediction from the actual thing. And then you're like, okay, we have that. Now we look at how much did each weight and like layer affect that output. And then you're like, if it affected it a lot, change it a lot because it's wrong. And essentially you then use that. It's like using like a calculation of like the how much change and how much of it, like how much like change there should be and stuff like that, using derivatives to then readjust all the weights. And so what you're doing is you're adjusting the weights to go in the right direction toward a better output. And that's what you're doing. Then you just keep rinsing and repeating that. It's like essentially like tweaking machinery to make it perform better. Like that's basically what backwards propagation is. You're like tweaking with the model to make it perform better.
What are some examples of neural networks?
Like I think we went over some last time, like predicting whether or not you have cancer. Like if you give a picture, right? The neural network can look at the picture and determine. So this is like radiology, and you're basically like, oh, the neural network identified a cluster, and like, oh, that could be cancer. And then, or for instance, like consumer analysis, like if you look at like people's internet data, you can be like, this person is more likely to buy this or not. Like YouTube algorithms or neural networks, like like basically like tons of things are just like deep learning neural networks. Like
we went over like some of them last time.
Yeah, but be wary. A lot of neural networks don't look like what I showed. What I showed is like the most basic neural network. A lot of neural networks get much more complicated and mathy than this. This is like this is considered like the most basic neural network. It's called like a MLP. I think it's multi-layer perceptron or something like that. But so this is like a simple neural network. They get more complicated from there. Here, let me try and see if I can pull up code for an example that I can then show you guys. Okay, so basically the model I'm going to show you is a model that predicts whether or not you have a disease. So it uses a sigmoid activation function, and it predicts whether or not you have like a disease based on the microbes in your gut. So essentially everyone's gut has like, we all have bacteria inside of us, and what this data set is essentially the measure of the like bacteria in people's gut. And then what I'm doing is predicting whether or not people have a disease based on their like gut biomes. So it's pretty cool. Okay, here, let me show this now. So data set is the inputs. All right. So let's look at this. So each row is a different person, and each column is a different bacteria, right? So look at that. We have all these different values. Now the values are basically between 0 and 1. Why? Because we normalize them. Remember how we went over data cleaning, how you normalize data so it's all within the same scale? So it's basically easier for the model to work with, so you don't have like to adjust for variance in scale. Does a more complicated network mean more layers and weights and nodes? Yes, technically you would call that like a deeper network if you have more layers. But what I also mean is there are different architectures. So there's things called like network architecture. So it's like the way that the networks are designed. So this one is pretty simple, right? So you have the layers and then you have the nodes. But in more complicated networks, like for instance, there's like convolutional neural networks, you have filters, and like it's like three-dimensional like weights, and it gets like more complicated with essentially how like the network works. So you have like input files, and then instead of doing like, because if you have an image, right, a picture is like x by y. It's no longer just a list of numbers. You're inputting like x by y. So then like for instance, like image network, instead of having a weight for each number, suddenly you have a set of weights for a portion of the picture. And then you also it gets more complicated, and then there's like sequence neural networks which basically work through time, and you have weights for like time, and then you basically it just like runs over and over again depending on the time. But yeah, so basically what we have is like the simplest network. So yeah, so let me just go over this again. And then if you look at the output, this is just the prediction of whether or not they have disease. 1 is yes, 0 is no. So that's what that is. So yeah, let's just run this real quick. Boom. So we're importing pandas and the Keras, which are the neural network stuff. So then we set the X and the Y to the data set and the Y to the output. Boom. Yep. Then we split it into the training set and the testing set. We've gone over this previously. It's basically like validating the data, making sure it's not like, okay, so now you see 548, 235. That's because 70-30 split. That's pretty common. So right here, what we're doing is we're creating a sequential model, and then we're gonna do so let's go over the layers right here, right? So you have a layer which has 12 nodes. That's what this dense 12 means. And then the input dimensions is 572 because we have 572 microbes. And then we're making it a ReLU activation function. So then the next layer is 15 nodes, ReLU activation function. Now what dropout is essentially, it's a way to make sure the model does, it's like a way to account for making, like helping the model not overfit. You're basically, it's like challenging the model by randomly dropping nodes to then make it have to work better with like less of its like nodes. So it helps it adapt better. And then another 15 layer node, and then the output node, which is 1 sigmoid. So you see in the intermediate layers, we did ReLU activation, but then when we get to the output, we want to predict 0 or 1. So then we do sigmoid. So because it's 0 or 1, the loss function is called binary cross entropy. We went over that last time. It's like the weird activation function with like log whatever plus negative, or like 1 minus log whatever, 1 minus, that's what that is. And then this is just an optimizer. And then yeah, so if we run this, you'll see that it creates the model, and then it compiles the model with that. So boom. So you see here, it's a model. This is this is just like TensorFlow stuff. So now we will run the model. Hold on, let me change this. Batch size, why don't we do 200, 200, and then we can do it for 150. Okay. So, all right, let's look here. Okay, so I'm gonna explain the terminology here. So if you guys see, each time it's like updating the model, right? So what batch size means is sometimes, so we don't really have to worry about batch size because what I'm running right now isn't a complicated model, But say some models are trained on data that's like millions, right? So you have like millions of training examples. If you run a single training example as 1 million, that's going to take a long time. And that's going to be very computationally heavy. So what batch size means is you split the data up into similarly distributed batches, right? Because if you take the batch that's pretty random, it should represent the overall data. So you essentially call it a batch size, and what an epoch is like how many times you so then you run the batches for every single batch inside of the data, and then so that way you have multiple like examples to then change the model instead of just one that takes a long time. And then an epoch is how many times you repeat that. So it's not really an issue for this analysis because we're not working with huge data. We have like 500 training examples, so it's not a big issue. But if you're working with huge data, that can become an issue. So then we can do like a plot to look at how it looks. So look at here. Each epoch is how many times we train the model. And what you see is that as the model gets trained more and more, the accuracy goes up. And you can see that the testing accuracy also goes up. So that's good. That means that our training accuracy and our testing accuracy goes up. And then we can look at the loss. And we see that it as the epochs go down, the training loss goes down, but the test loss goes up a little bit, which might mean we're starting to overfit. So we might want to account for that. But do you guys like see how, for instance, if we look up here, we see that each epoch, the loss starts to go down. Do you guys see that it's going down slowly and slowly? That's what we mean when we say gradient descent, which means as we keep training our model, we keep adjusting the weights to make it perform better. So you can see that we get up to basically like 90% accuracy in our model, which is pretty good. And yeah, so that's kind of, and then yeah, so this is like an example of the model.
But if the model like loss goes up, does it mean like we're overfitting?
Yeah, exactly. That's what I was saying. That's like that's exactly what I was saying. So I was saying is like essentially it's not a good sign that our testing loss suddenly jumps up. So that actually that's like something that happens, which is if you overtrain the model on the testing data, it will get like to basically perfectly on the testing data, but suddenly it doesn't apply well to other data, which is what like it shows. So what that probably means is we chose the model and weights that work super well in the training set, but don't perform nearly as well in the test set, which is not what we want. So maybe we would go back to epoch, say 50, right? Because that's where it looks like where it's the lowest, like maybe epoch 50, 55. And we would go look at that model and be like, at that model, how was that? Like, was it good? Like, was it good enough? So we can go up here, 50, 55. Yeah, that's pretty good. You see like the intersection where the accuracy is kind of the same. But yeah, so yeah, we basically probably wouldn't want to use this model for anything real. It's just like an example.
So like we learned like about like activation functions, right?
Mm-hmm.
And like we learned about the sigmoid activation function.
Yeah.
Like so like what and sigmoid is used for like zeros and ones and yes and no's, right?
Mm-hmm.
So yeah. Could you like explain like what some other like activation functions can do? Like what are they used for?
Yeah, hold on. So one is like, I don't know if you call it an activation function or like an output function, but SoftMax, what it basically is it's assigning probabilities to outputs. So you have like multiple outputs or like quote unquote classes, and then you're like, what is the probability it is of each one? So that'd be like multi-classification, not binary classification. Binary classification, you can use sigmoid because it's either 1 or 0. But if it's multiple, you would need to do like probabilities and then choose the highest probabilities. ReLU, or there's ReLU, or there's linear. These activation functions are mostly for looking at like within the layers. Like these are usually used inside of layers. Sigmoid is used for binary classification going over. ReLU might be used for linear predictions, right? So if you're predicting values that are only positive, you don't need to worry about negative numbers. So you might use ReLU. So you only look at numbers greater than 0. Or you could just use linear and then just take the error. But yeah, so these are some different functions. And then there's or sometimes you don't, like on the last layer you might not have activation functions. You might just literally just have the output, like you just take the numbers it outputted. But it really depends on the network and like what type of task you're doing. Because yeah, but
what would MaxOut be used for?
I have no idea. I actually never used that one before. I only really use ReLU and sigmoid because yeah. No, that's the thing. It's like, because this is a fairly new field-ish. Like we have the computational power to do it now. So people are like inventing new stuff and trying new things. So people are constantly trying new things. But yeah, I don't think max out is something that people really use.
Neural networks, is it like doesn't it acts like a brain for like a computer kind of?
Yeah, well, it's like a brain because it's making decisions like a brain, right? So like with us, right? Our inputs are our senses, right? What we see, what we hear, what we taste, what we smell, and then our thoughts are like our neurons firing, right? Because if we really get down to how we think, it's just our neurons firing and doing stuff. And then that leads to the outputs, which is like our decisions, like what we decide, what we see. Like for instance, with our sight, we don't like necessarily just see, right? So what it is like it's light comes into our eyes, which hits like our cells or whatever. That goes to our brain. Our brain analyzes that and then tells us what we see.
Yeah.
Right? So that's basically, think of it, that's kind of like a neural network, right? Because you have the inputs, the light, goes through our brain, then the outputs is what we see. Alrighty. Well, I will see you guys next week. Farewell. Stay safe. And see you guys. Thanks for coming.